Yeah. So, very good evening to everyone. Uh, Welcome back to the TA live sessions for artificial intelligence search methods for problem solving for NPTEL. Am I audible and is the screen visible clearly?
Yes, sir.
Okay, great. So, yeah, very good evening and welcome all. So, we can get started without further ado. So, before starting, so is there any particular specific doubt from the previous live session that you would like to discuss or address? No, okay. Okay, then that's good. If there's any doubt, please let me know in the discussion forum. Yeah, so we can get started with this week's content. So, uh,
Hello.
yeah,
Yeah, sir. Can we discuss question on space state research search method that is available on week 2 assignment?
uh, the DFS and BFS topics you mean?
No, sir. The bucket problem.
The water jug problem.
Yes, yes, sir. Yes, sir.
Okay, so had you attended the previous live session?
Yeah, sir. I had attended. Actually, I'm not able to find out the proper answer. That how many proper states we required. You just brief
Okay.
on that question, sir. That's it. I get an idea on that then.
Okay, sure. So let me do one thing. So what we can do is let us proceed with the week two questions, and in the end we can have a quick revision of that topic. Is that be will that be okay?
Yeah, sir. Thank you so much.
Yeah. So Vikram, so if you yeah, I guess they have the NPTEL team has uploaded the week one slides and the recordings a bit late. So I think it is available now. If you go to your Swayam portal, I'll just show it to you. One second. Uh, So if you go here, no, where you have all these weak videos listed, so there's a problem solving session section over here. And if you click on this link, you will have access to all the recordings as well as the slides. So you can use that. Okay. Varun, yes, we will be discussing questions related to BFS and DFS. So let's get started. I don't have questions on DFID today, but I guess if you understand BFS and DFS, it won't be much of an issue kind of extending it to DFID. So yeah, let's get started. So let's say this is the first let's say a state space that is given to you. Okay, so just have a look at it and familiarize yourself with it. So the next two questions will be based on this. uh, so first of all, does do you so is the relation between this move gen table listed over here and the state space like clear to all of you?
Yeah.
Okay, that's great. So let's move on to the question.
Hello, sir.
Yeah, Anukul, tell me.
Sir, can we get the recording of this lecture?
Yeah, the recordings will be made available to you. That's what I was saying just now. So on Swayam, there is a particular section called problem solving session. Uh,
Okay.
there you can access the links for the slides as well as the recording for all the
The,
sessions
the
that you.
last the last class that you guys taken, is it available also there?
Yeah, I guess they have made it available now. So if you check it now, you'll find the link over there.
Okay, sir. Okay. Thank you.
Yeah. Okay, so this is the question you have on your screen right now. So you saw the state space just now. So which of these trees do you think is the search trees? Would be the DFS search tree? Okay, so we have an answer. Hariharan says it's option D. Okay, we have another uh, contender for option 4. one person says it's option A. So can you guys like share your thought process? Why do you think a particular answer is the correct answer? What do you think?
May I go first?
Yeah, sure. Go ahead.
So basically, in depth first search, what I understood is that first we go down the depth of the tree, and after we have searched like till the very end from one of the nodes, like from S, we have three C A B. So like first we'll take one of those like C, and then we'll go down till the very end, and then come back up, and then go down from A, and then go down from B.
Okay, so so you guys are familiar with what data structure DFS uses, right? Uh,
Yeah, stack.
Stack. Okay, so how does stack function? So we add elements on, keep adding elements on the front or the top, right? So something like
Yes.
this. Let's say this is our stack. You have, let's say, something over here. So the new element, when it is added on top of the previous element, let's say. And when it is removed again, it is also removed from the top. Something like this. And it differs from a queue in the sense that, so this is a stack, and this would be a queue. So here you add elements from the rear end, and let's say, so let's say this will be an A here, and let's say this is something else, and when you take out elements, it's from the front end. So this is the basic difference between a stack and a queue. And so let's go back to our problem. So let's look at what the actual answer is in this case. So the correct answer would be tree 4. And why that is so? So look at the way your open list is functioning. Okay. So let's say you start with S. Okay. And at that moment, your open list would consist of what? C, A, and B. Right? So it would be something like this. You have your C over here. And you have already taken out S. S is in the closed list. Okay. By this point. So let's say you take out C first, then explore C. Once you explore C, then you consult the corresponding move gen table and see F, B, and S are the possible states that it could go to. But C, S is already in closed, and B is already in our open list. So we add F on top. So we explore F. Okay, next. Is it clear until this point? Any doubts till this point? Okay, great. Yeah, so you see, until this point, tree 4 and tree 1 are similar, right? Now, what happens after this? So once you explore F, you consult the move gen table. Okay, so what are the possible states it could go to from F? B, E, D, C, H are the possible things, right? Now, B is already in the open list, okay? E is a possible contender, so you add E to the open list, okay? D is also a possible contender, and C is already in the open list, I guess by this point. It's in the closed list, and H. So you see the order in which this it appears in this move gen list, this E D H is the order in which you put it inside the stack. Okay. So after you have reformed the open list after moving on from F, the first node that you will explore would be E, not H. Okay, that's why tree 1 is not the correct answer in this case, and tree 4 is the correct answer. So if you go to E, then you form the open list and closed list again. You see after E there's no further path. So you go back, then explore D, and then you go to H, then explore I, J, and finally G. So this is the actual search tree in case of DFS. Okay, so any doubt about this?
Sir,
Yeah.
sir, after F, why they are choosing H only and why not E and D?
No, that's the thing. After F, we are choosing E. That is the correct way to proceed in DFS. Okay,
So why we have to choose E first? Why not H?
because one second. If you see this move gen table, okay, so
Yes, sir.
corresponding to F, what do we have? B, E, D, C, H. Okay, now
Yes, sir.
we don't need to include B because B is already in the open list at this point. Okay,
Yes.
E is
Yes,
not,
sir.
D is not, and C is already in the closed list. Okay, and H is
Yes.
not. So E, D, and H are the possible candidates that we have to add to our open.
Yes.
Okay, and the order in which we add it to our stack is basically the same order in which this appears in this list, EDH. So when suppose this is the stack configuration that we have, okay, something we have over here, some initial things we have, okay, and when we add on top of this, E is here, D is here, and H is here. Okay, so in the
Yes.
next step, when we take out one element to explore, E will come out first. So that's why after F we are going to E first, not H.
Okay, sir.
Okay, so we'll do one thing. We'll discuss another DFS problem and we'll solve it step by step, and it will be a bit of simpler state space than this one. So I guess after discussing that, it will be uh, much clearer. Okay, so yeah, so Soumyadeep, I guess you had asked a question in the starting, so I'll come to that. Okay, just remind me if I miss it, but I have it in my head, so we'll address it at the end. So this question is clear, right? Or any doubt? Okay, great. So if this is clear, let's move on to the second question. And which of these do you think is the BFS search tree now? These are the same four trees you saw just now, but which of these would be the BFS search tree now?
3.
Three. Okay. Any other answers? Or does everyone agree that it's three? Okay, so we have some people saying it's two. Okay, so would any of you like to explain your thought process? Why do you think it's B?
In 3, it's traveling through its depths first and then going to the child nodes. So that's why I'm saying it's 3.
Okay. And the other party who says it's the option, who says the second three? Would anyone like to volunteer? Okay, okay, so let's discuss it. So here, instead of stack, we have a queue structure, right? So we start with S, okay, and then we include A, B, and C, C, A, and B basically. So it's something like this. So we have our queue, C, A, and B. Now do you get a hint? Which one might be the right option? See, remember in Q, the one in the front end is taken out first, not, and the way it is added is from the behind, not from the front. Yeah, so let's see the answer. The answer would be tree 2, because you see, this is our Q. Okay, this is the front end, this is the rear end, and we take out C, and then we explore C first, then we explore A and B, and so on and so forth. So that itself gives away that it's the second tree, CAB, in this order, not ABC. Was that any helpful, or is there still any doubt?
No, sir, clear.
Okay, great.
Our answer
Yeah,
was
yeah.
J. Okay.
Sorry, Ajay, I couldn't get you. Can you please repeat?
Tree 2, it got stopped when it reached to J after H, I and then J. That
Yeah.
is why it has stopped.
Yeah, I mean, it stopped when it reached its goal state, its G state, which it intended to reach.
Hmm.
Yeah.
So why the tree is not correct? Because it got stopped after A, B, C, E, D, F, and H. It got the answer from the H. Then that is why it got stopped on the H.
No, no, you don't
Why
have to
three?
look at when it got stopped. You can just figure it out from the first level of the tree. See, the top level here contains S, okay, in both tree 2 and tree 3. And then in the next level, you have the tree 2 exploring C, A, and B, not A, not A, B, and C. And C, A, and B is the correct order in which the BFS was supposed to explore. So you don't need to go down and see where it is stopping. You can deduce it from here itself.
Got it. Got it.
Yeah. So what we'll do is we'll take a simple example and solve both DFS and BFS step by step. So by the end of it, I hope it will be much clearer to everyone. So let's do that. So this is the simple state space and the simple move gen table that we will be dealing with for the next couple of questions. So just familiarize yourself with it. Hariharan, I couldn't understand your question. What are we comparing with BFS search tree and solve it? It's like, can you elaborate a bit? Do you mean to say that? Okay, so first the algorithm searches around its start point and then it moves. See, if that kind of suits your understanding, then you can go ahead with it. But I usually like to interpret it in terms of the data structure that the algorithm is using now. So that uh, makes it much easier, at least for me, as per my understanding, to understand uh, which search tree we are kind of progressing into, or what are the steps we are following to uh, reach the final search tree. Yeah. So, okay, so I hope that's clear. So let's solve BFS first. Okay. So we have this. Let me just move it. Give me a minute.
Sir, you said that the data structure determines whether the DFS or BFS is to be used. So, I mean, how to determine based on the data structure which algorithm is to be followed?
No, no, I guess what I meant to say is the data structure that you use depends on what algorithm you are using, not the other way around. So
Okay.
if you are to find a DFS search tree, just remember that you would have arrived at the search tree using a stack. And if you are looking for a BFS search tree, just remember that you would have used a queue instead. So if you kind of, kind of trace it back and see how it would have happened, you'll get to the answer in a simpler way is what I was trying to say.
Got it. Thank you.
Yeah, Varun, are you referring to the previous search tree question? So we can just have a quick look at that. So the correct answer was tree 2.
So can
Okay.
you explain the question at
Uh,
the instance?
this
This question,
question,
can you explain?
third question.
Yes,
Uh,
yes.
sure, sure. Yeah, I'll explain it. Just give me a minute, okay? I'm trying to figure out something.
Sir,
Yeah, tell me.
sir, in these types of questions, the graph which is given in the question, is there any role of that graph also in solving the question?
Uh, which question do you mean? This third question?
Yeah, third question, second question, all the graph. I only use this table for solving. So, is there any role of this graph also?
Yeah, so basically you see the table is one interpretation of this graph. So both these things basically are conveying the same information. So if you compare it, if you see uh, corresponding to S, you have A and B in the move chain, right? In the table.
Yes,
And in the graph, what are the nodes that are connected to S? Again, A and B, right?
yes, sir.
That is what is the information is kind of displayed in this graph as well as in this table. Similarly, if you look at, let's say, C, then E, A, and D and B are the states listed, and let's check in the graph. So what are the states connected to C? E, A, B, and D,
Yes,
right?
yes, sir.
Yeah, that's what it is. So you can choose to refer to either the graph or the table. They both have the same information.
Okay, sir.
Yeah. Okay, so we already have a couple of answers. So thanks for the answers, guys. So we'll discuss it and we'll see what the correct answer is. Uh, so uh, there's no book that I'm referring to for these questions. But I guess the best if you want to study about stacks and queues and any let's say any portal like Geeks for Geeks would be an ideal place to start if you are new to it. It won't go into too much detail and it will kind of give a nice intuitive idea to you. So that's what I would suggest. As for these questions are not from any book. These are taken from the previous iterations of the course. Okay, so without further delay, let's just discuss it. Give me a moment. Yeah, so we are trying to solve the BFS. And by the way, so I'll be using a very simplistic way. So the way I'm trying to solve it is just for to make you guys understand the exact algorithmic steps may be a bit more detailed or complicated, but don't worry about that. So this is just to give you a kind of an idea of how we can approach the solution. Okay. So let's say this is our open list and this is our closed list. To begin with, since we are starting from S, this is the only thing we have in open and closed list is empty. Okay. Now we explore S. So can you suggest what would be the open list at this point? Anyone?
A and B.
A and B in that order,
A.
right? Correct. So we will have A and B and closed list will have S.
X.
Right. Okay. Now, so what can be the next step? Which node will we explore next? What do you think?
C1.
A. A.
A, right, because we are using a stack. So our closed list at this point would be
Yes.
AS. And since this is a stack, so let's refer to our move gen table. So C and S are the possible candidates. Okay, out of which S is already
So from
enclosed.
A, choosing B, A instead of B,
Sorry,
why we are choosing exploring A instead of B?
because this is a stack structure, if you remember. Oh, sorry, it's a queue structure. I'm very sorry for that. It's a queue structure because we are doing a BFS search. Okay, so let's say this is our
Okay,
queue.
sir.
So we are taking out from this end and we are adding in this end. Okay, in the open list.
Okay, sir, understood.
Okay. Okay, yeah. So coming back, so S is already enclosed, so we don't need to consider it. So C is there, right? So where will C be inserted? What will be the open list looking like in this case?
BC.
B and C.
Yeah, it will be B and C, right?
அண்ணா வாங்க அப்புறம் எப்படி இருக்கீங்க நான் இப்பதான் வந்தேன் அந்த மாமா
So
கூட்டு போலான்ட்டு
I
வந்தேன்
sincerely request to mute
நீங்க எங்க
yourself
இந்த
if you
சைடு
don't have a question. Okay. Yeah, thanks. Yeah, Hariharan, so we are not considering the current node parent node version for this particular explanation because that just, clutters the explanation. I'm just using the current with the notation without the parent node. So you can just extrapolate it to current node parent node explanation. If there is any confusion, do let me know. Yeah, so this is our open list. So what state are we going to explore next? Which one do you think?
So B.
B, correct. Yeah. So this will be then BAS, right? And let's see B. So C is already in our open list and S is already in our closed list. So only thing we have to add is D. So is this correct?
No, it should be CD.
CD. CD.
It
B and
should be
B.
C.
Yeah. Yeah. This is CD. So next what are we going to explore? C, right? Is it correct? The closed list now.
Yes.
Yes, sir.
Now E is new. A is already in the closed list. D is already in the open list and B is already in the closed list. Now what will the open list look like?
DE.
Yeah, this looks like B. Just yeah. Yeah. Next we go to D. So this will be D C B A S. Okay. And okay, so this will have E in the front most probably. And what will be the
G.
other things?
G. G.
G. Are you
G.
sure? C. F is
Sure,
new.
G.
F, is it F?
Yeah. So C. C is already in the closed list. F and G are the new things. So we have to include it in that order, right?
Yes.
Is it kind of alphabetical order? You're going
No,
A,
it's
B,
not
C, D.
alphabetic order. It's just give me a moment. Okay. Just give me a moment.
Sir, I think we should be adding the children of D, and that will make the current open list as E and G, because C and B are already in the closed list. The one that
Yeah,
you are
yeah.
saying is for the next one.
Yeah, that's very right. Actually, I made a mistake. So very sorry about that, and very thank you for pointing it out, because I was thinking that there's something going wrong over here. Okay, so
Means at a time we cannot write the two nodes into the open list, right? Or more than two.
no, that's not the case. We can add it, but
And
then it'll just have to be in the order it is given in the movegen function list. Okay, so this was, I guess, correctly written, and this would be what, E, and so we'll have to look at D, the corresponding list for D, right? So G will be there. So yeah, you guys were correct. I'm very sorry
So I
for.
think you have to share the Jamboard.
Oh, is it? Oh, okay. Yeah, is it visible now?
Yeah,
Yes, sir.
now it's fine.
Okay, great. Okay, yeah. So sorry for that mistake. I guess I just lost track. And so next, what is? So we'll explore E, right? E, D,
Sir,
C.
can you do it from the beginning?
Sorry.
Can you solve it once again from the beginning?
Yeah, I'll do that. I'll just finish where we are at this point, okay? And then we'll continue
Okay.
from the start. And I'll show a more kind of a better, not a handwritten this one, a better answer to this. Okay, anyway, so this would be something like, what do you think?
GF.
GS. Yes.
Yeah. So this is the point where we have reached what the answer was demanding. So what our question was saying is, at the instance when the BFS finds G. So now the BFS has found G. Okay. So the closed list is EDCBAS. Did we get that? We
Yes,
got
sir.
that, right? Yeah. Okay. So just for the person who was asking a clearer explanation, so let's start from the beginning. Okay. So I'll just go through it quickly. So we started with the S node. Okay. And at this point, the closed list was empty. Then we had a look at what was the open list in this case. When S was added to the closed list, that is S was explored, A and B, these were the nodes that were added to the open list in that order. Okay, A and A comma B. Okay, next A will be explored because it will be taken out from here, the node to be explored. So A will be explored next and it will be added to the closed list. And let's look at the neighbors of A. So we have C and S, out of which S is already in the closed list. So we have to add C. C will get added from the rear end. So this will be BC. And the closed list at this
Sir,
point is,
sir, please.
yeah,
We are exploring A.
yeah, we were exploring A.
We are exploring A,
Yeah,
and A and B, A and S are in the closed list.
See, so let me just delete these things. So when you are exploring A,
Yes.
then what are the possible states that it could go to? C and S, right? So
Yes. C and yes.
at this point, look at this closed list. It had S, and now you are exploring, sorry, now you are exploring A, so A will get added and it will be AS. Okay, and similarly, the open list will get updated, it will be BC. Okay, because from A, the possible states you can go to are C and S, and we don't want S because S is already there in the closed list. So the only option left is C. So you add C from the back end, and and the open list becomes BC. Is that clear?
Yes, sir. It's clear.
Yeah. Then we explore B. Okay, and B is added to the closed list similarly. And for what are the options from B? C, D, and S. Okay, C is already in the open list, so we don't need to see that. S is already in the closed list. D is the only thing left, so we add D from the back, and the list becomes CD.
Sir, sorry for the interruption,
Yeah, tell me.
but uh, is it necessary to start with A or we can go with B also?
No, we started with S, right? We didn't start with A.
Yeah, yes, sir. After S, we will be having two options. That is to go with A or to go with the node B. Then we choose A. So it is compulsory to go with the first one, or it is just for depend on our choice.
So it is because we are using the queue data structure, right? So in queue, when you insert a new element, it is from the back side, and when you remove a new element, it is from the front side. Okay, like
Okay.
what would happen in a queue for a movie theater? So people keep joining the queue from the back, right? And people
Okay, sir.
buy ticket and go into the hall from the into the theater from the front of the queue, right?
Yes.
It's similar to that. So since this is our queue, say this is A and B at this point, this is our
Yes,
open
sir.
list. Okay. So that's why we are exploring A before B because A is in the front of B.
Okay, sir. Thank you.
Yeah. So, okay, so we were at this stage. CD was the open list. Should I get into the further explanation or is it clear?
Is it possible that after S,
Uh-huh.
B node is traversed, then A node is traversed? Like the first set, A and B, if we reverse that to B and A, then
So you're saying if instead of this, it was BA. That's what you're saying, right?
yes, yeah.
Yeah, in that case, we would have explored B first.
That combination is also possible, right?
Yeah, that is possible. So that depends on how you define your move gen function.
Got it.
Yeah,
Sir,
yeah, tell me.
hello. I want to say that means every time I have to take a head element of the list, right?
Yeah, that's right.
Okay.
In closed list, the new node to be added in the head or tail.
So in the closed list, you are always adding it in the front, you see. So first S was explored, then you explored A, it was added in the front, then you explored B, it was added in the front. So you continue like that. Okay.
So,
Okay.
sir, the closed list is a stack, right? If we are adding from the front, or will we call it a queue?
uh, you can say it's a stack. just the difference. The thing is that we are not taking out anything from the closed list for BFS or DFS for that matter. So we're just adding stuff and you're adding it to the front.
Okay, sir. So the open list, sir, can we define it using like two stacks also? Like if we want to go for a queue, so that this could be possibility, right, sir? That if we make it in the form of two stacks.
Uh, so how would you use those two stacks for? Can you elaborate a bit?
Like, sir, that because queues have to have entries from the rear end and removal from the front end. So to simulate a queue, like actually saw that we could use two stacks also to, have an entry from one of the stacks and then you copy it to the other and so you remove it from the other one. So it kind of follows the queue, rule. The queue rule can be followed that way.
Okay, so you mean to say that you want to use stacks for implementing the queue, right?
Yeah, two stacks can be used to simulate the queue, I think, like if it's possible here. I was
Uh,
asking that if that's a possibility.
I mean, if that's possible to implement, you can use it, but then why would you go ahead and complicate things, right? So you could simply implement a queue where elements are added from the back and removed from the front, right?
Yes, sir. I was just asking as a possibility.
Yeah, I mean, if that's possible, you can surely use that. But as a general rule, we try to avoid any complications. So the simplest way is the best way to go, I would say.
Okay, sir.
Yeah. Okay, so there were a number of chat messages. Let me just go through them just to see whether I missed anything. Yeah, so we missed the children of D in that example. Thanks for pointing that out. I guess I addressed this. So, yeah, once again, if you don't have it out, please mute yourself. Yeah. So, in general, it is preferred to write the closed layer ending in S, the way we just discussed. So that is the way to go, Chikul. If we add node pairs, should we add S null or S nil? Uh, I mean, it's kind of same. So null and nil don't really matter in this case. You just mean to represent that S doesn't have a parent of its own. So either is fine.
Sir,
Yeah, Somadeep, tell me.
what is the difference between a DFS and depth-bound DFS?
Yeah, thanks for reminding me. So the difference is that in depth bound DFS, you are setting a limit to the depth to which you are going to explore. If you remember the search tree, we went from S to A to certain depths, right? Till until we reach the goal state. So this was a simple state space, right? So you could go to a certain depth and find G. But if we have a very large search space or a state space, so one strategy you could use is explore until a certain depth, let's say until 3 levels, and then you see that we have not yet reached the goal state. So you go back and try another depth. Just this way. I mean, this is a very high level kind of explanation of what you were asking.
According to the algorithm, the depth bound should increase by 1 each time.
Yeah.
So then how can depth be equal to depth bound at any moment so that it will backtrack?
I mean, you can have a variable that kind of estimates your depth, right? You can use that to see what depth you're currently exploring.
So means in actual programming we can set the depth bound.
Yeah, you can do that if you are interested in implementing it.
Okay.
Yeah. Okay, so yeah, thanks for reminding. I will have a quick look at the state space problem again. So let's just quickly go through the remaining questions. There aren't that many. So this question is, I guess, already answered because we just discussed the BFS whole step-by-step procedure. So what was the open list in our case that we got? It was G comma F when we discovered G, right? So the answer was G comma F. Yeah.
Hello, sir. Why do we explore that E node?
Which node?
So that E, actually we are already reached the G node after exploring the, I guess, D. So we should not be exploring the E node now.
No. See, after exploring D, the open list is something like this, E comma G, right? So since E is at the front, you have to explore E first before arriving at G. So it does not matter if the goal state is somewhere is in the open list, it should be at a point from where it is accessible. That's why the question says that at the instance when BFS finds G, right?
Okay. Thank you.
Yeah. Okay, so time for DFS now. So let's solve DFS from the beginning. Yeah. So the difference here is that you insert at the front and you take out from the front, like in a stack. Okay. With that in mind, S is the start node. Okay. And the closed list is empty. And then we form the open list A comma B like in the previous case, and the closed list is S. Now we explore A now. Okay, because A is in the front, so closed list is A comma S, and the way it is added is C is to be added, right? Because S is already in the closed list, so C is added in the front, unlike in BFS where C was added at the back. If you remember, in DFS C is added in the front.
Yes.
Yes, so it becomes C and B, the open list. Next we explore C, so your closed list becomes C comma A comma S. And from C, what are the states that we could go to? E is a new state, A is already in the closed list, D is new, and B is already in the open list. So you add E comma D in that order in the front. So your list becomes EDB. Is this clear?
Yes, sir.
Okay, great. So then next you explore E. So your closed list becomes ECAS, and you add F comma G in the beginning. So your open list becomes FGDB. Next you explore F. So your closed list becomes FECAS, and you go to A, and A is already in the closed list and E is also already in the closed list, so you don't need to add anything to your open list. So your open list would simply be GDB, and you have reached G. So this is where your DFS terminates. So was this step by step clear, or any issue in the DFS case?
So when we were exploring this C node, then why was the addition of E then D was performed? Like, for if you're saying it's a stack, then shouldn't it be like the E should go and after that D should be added on top of that?
Yeah, see, so E is comes first over here in this move gen list, right? From C, the possible next stage that you could go to in this list, E comes before D. That's why in this order it is inserted in the open list.
So, sir, for BFS, it should have been DEB.
BFS, it in the BFS example. In which step exactly? Can you
In
point
the
out?
exploration of C.
Okay, we are exploring C.
Yes, sir. So, in that case, we would be adding like only the first one that we get, right? The D node would be added then.
No, see,
Or
when we are exploring C, D is already a part of the open list. If you see here, we have C comma D. Okay, so you don't need to consider D, A or B because A and B at this point are already in the closed list. So the only thing you need to add is E, which you add to the back. Okay.
Okay, sir. Yeah.
Yeah. Okay, so there is a doubt that says how to write paths for DFS and BFS. So Vikram, if you want to write the paths, then you have to include the parent node as well as the current node that you're exploring. So in that way, you can trace back your steps to see. For example, let me just show you a simple example. Suppose you wanted to do that in case of DFS, right? So instead of having just S or A and B over here, you would have a node pair, something like S and nil, let's say, to start with, to say that S does not have a parent in its search tree. So S is the root. And so after S, when you explore A, let's say, because you are exploring A after S, the way you would make an entry in the closed list would be something like A with a parent S and S with a parent nil. Something like this, this list would be. So this is the parent and this is your child. So doing like this, when you arrive at G would have some parent over here, right? So you can say that G had some parent that you will write over here. Then you will see what this parent had another parent, let's say P1. So you will keep doing this until you reach S, and this way you can trace the path. Okay. Okay. Yeah. So I guess we have just found out the answers to the next two questions, but let's, for the sake of it, let's just see. So at the instance when DFS finds G, the closed list is FECAS, right? This is the closed list. This is what it looks like. And I guess this is our answer. FECAS. And what does the open list look like when the DFS finds G? It's GDB. So that is our answer. So these were the questions for this week, right? So I hope these are clear. Can you just give me a yes or no if everything is clear?
Yes, sir. Yes, sir.
Okay,
Clear,
great.
sir.
Okay. So I'll just quickly discuss the state space issue that you guys had asked me to discuss. Okay, so let's say that we have a 752 water jug problem. Okay, so the first jug has 7 liters capacity, the second jug has 5 liters capacity, and the third jug has 2-liter capacity. Let's just call it J1, J2, and J3. And suppose you start from the state S00. That is, your first jug has 7 liters and the other two jugs don't have any water in it. So from here, what are the different states you could go to? Let's say you make a transfer of 2 liters from this one to the third jug. Okay. Then this would be 5, 0, 2, right? Another possibility is that you transferred 5 liters from the first to the second jug. Then this would be 2, 5, 0. Is this clear?
No, no. 250. From where the 5 has come?
So you have transferred 5 liters from here, from the first jug to the second jug. Basically, you have not
Okay,
exactly
okay,
measured 5 liters and then transferred. You kept on pouring from the first jug to the second jug
got it.
until it got filled. So you had 5 liters that way. Okay. So
Got it.
similarly, from here you can move to certain other states as well, right? So suppose you want to move you kept pouring from the first, you are in this state now 502, and you kept pouring from the first jug to the second jug. So let's say you have something like 052 now. So the first jug is empty, you have poured all its water into the second jug and 2 liters in the third jug as it was previously. Similarly, from here you could go to another state. Okay, so if you transfer this 2 liters from the first jug into the third jug, what is the arrangement that you will have? 052, right? Because the first jug would be empty, this would be 5 and this would be 2, right?
Right.
Yeah. So similarly, you can keep transferring and seeing what are the possible valid states you got. So if you go back to the previous live session, we saw one such path which led us from 700 to 151, this arrangement, following a number of steps. So suppose you followed a number of steps and you reach a state that is 151. From here you can go to another state. You can transfer this 5 liter from the second to the first one. So you have something like a 601, right? So you keep on thinking or trying to see what are the possible states you can reach via different possible transfers of this water from one jug to another. And in this way, if you keep exploring it, you will see that if you start at 700 state, there will be 14 such valid states that you will get in the state space. Okay. And apart from these 14 states, you will see there are 4 other states that uh, you, let me just open that particular slide for you. One second. Yeah, is this visible? Yeah, so you see here there are these 14 states that you found by various transfers of water, okay, in the outer circle. And there inside there are these blue states, this 331, 421, 511 and 241, from which, following a certain number of paths, you can reach the 700 states, the initial. But from 700 there is no direct way to reach these particular states, these blue states. So if you add these 4 states, total number becomes 18. So this was just an example of a simple state space 752 water jug problem, which had 14 or 18 if you consider these 4 states as well. This total number of states, a very small number of states. There can be problems like the traveling salesman problem, where there can be as many as hundreds or 200s or thousands of states. Okay, so that you cannot solve by hand, but a simple simple problem like water jug you can solve by hand also. So was that any helpful, the person who had raised this question? You can unmute yourself and speak up if you have a doubt.
So what would be the common algorithm which can be used for finding out these states other than just trying it out?
See, so this simple example was just to motivate the fact to you that what are the different representations of state and that there could be a high number of states, and so you need algorithms to explore that search space. Whether there is an algorithm to enlist a total number of states, I guess that would be very problem specific. So if you have a certain problem, you might follow a certain implementation or something to enlist all possible valid states that could be. But I don't think there's a specific dedicated algorithm that could work for all problems.
Okay, sir.
Yeah. Okay. Yeah, so Satish, the slides will be shared in the same link that I just pointed you to at the start of the session on the problem solving. There's a link to a Google Sheet over there. You'll find the links to all week's slides and YouTube like this recording videos as and when we conduct these live sessions. So
Sir, doubt, sir.
yeah, tell me.
Sir, can you explain once again how the four states are come? Please once again explain, sir.
Yeah. So if you say you are in the 331 state, okay, from 331, you can go to 232, then 232 to 250, then 700. But from 700, there is no direct way to reach 331 or indirect way for that matter, because this arrow points not in the reverse direction. So just try it out yourself and see if there are any possible ways to transfer water between these two states so that you are reaching one state from the another. Just try it out yourself and have a look and see.
Assignment, there
Yeah.
was one uh, in which they had given the state space tree for a similar water jug problem, and they had asked that how many number of states can be reached from the start states in 0 moves, 1 moves, or more moves. So if
Okay.
we go and calculate that by hand, I think it would be really difficult.
For the same 752 problem?
No, they had changed it to 10. I guess it was 853.
Okay, so yeah, I guess 853 wouldn't be that difficult, so you can still try it out. Uh, yeah, you can still
Yeah,
try it out.
but the thing is that they ask like from one move, so it will be like two states, and then from two moves, it will be more, and then like if we keep on going on, wouldn't that take a lot of time to calculate? Like, isn't there some formula or something like that for
Uh,
that?
I don't think so. So it would be good if you can explore it, manually, because that will also help you understand the how this problem is structured, basically the restrictions and the working of the problem. So I guess that was the intention behind the question. Uh,
Okay,
yeah.
thank you.
So Hariharan, the hill climbing algorithm, I guess, is from week 3. So I'll prefer to discuss it or any doubt related to it in the next live session when we discuss week 3. Or if you
Sir,
have something specific, you can just post it in the discussion forum, and I guess it will be addressed by Bhaskar and sir.
sir, doubt, sir.
Yeah, tell me.
Sir, if the starting point is 700, the end point is 322. If they're asking the how many steps to reach the 322, then we consider 052, 502, 520, then 322. We have four steps, sir.
From 700 to 322 you want to go, right? Okay, so from
Yes, sir.
700 you can go to 502 and then 520 and then 322. So there are 3 steps, right? Not 4.
Okay, sir.
Yeah.
Sir, then consider from 700, 502, 520, and also 322, sir.
Yeah, so you are moving from 700 to 502, that is one transfer. Then you are moving from 502 to 520, that is the second transfer. And then 520 to 322, that is the third transfer, right?
Okay, sir. Thank you, sir.
Yeah.
Sir,
Yeah. Yeah, 1 second, Subhashi. So Harshita, so this question that you're asking was, I guess it was raised in the discussion forum as well, and Bhaskaran sir had addressed it, so I would refer you to that. Yeah, yeah, Subhashi, you were about to ask something.
Yes, sir. I forget that. How can we reach the 331 state from 700? Not in the indirectly.
No, that is the point. No, that is the issue. That these four states, you can't reach from 700. That is the issue here.
So if I move from 232 to 331, then I have only 7, 5, and 2. So
No, no.
how?
See, from 232, how will you move to 331?
Yes, sir.
Yeah, that is the issue. No, you can't specifically take out, uh, you know, a specific volume of water and form the arrangement of 331. So just explore it and see what happens. So I guess we are already past the time. So if there are no further doubts, I'll just close the session and
Sir,
yeah.
we were not able to enter this live session from the starting. So can we get the live session has recorded?
Yeah, it will be available. So if you go to your Swayam portal and you see that there is a, can you see it? There is a problem solving session over here. If you just
Yes.
click, if you just click on this link, it will lead you to the corresponding links to every week's recordings as well as the slides.
Okay, sir. Thank you, sir.
Okay. Okay, so I guess I will conclude and thank you so much for attending and see you next week.
Thank you, sir.
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 Thank you, sir.